Okay, suppose we have to prove this. This is an identity. Assuming that this is invertible, A is invertible, and A plus B C transpose is also invertible, then this identity holds. Why do I have 1 plus this in the denominator? Because it's a scalar. Both sides are matrices. The numerator of this term is a matrix, but it's divided by a scalar. You cannot divide a scalar or vector or a matrix by a vector or a matrix. Okay, so when you have something in the denominator, make sure that it's a scalar quantity. 1 is a scalar here. C transpose A inverse B is also, if you look at the dimensions, it will give you a scalar, this product. Okay? So let's prove it. The best way to prove it, since this is invertible, I'll pre-multiply both sides with A plus BC transpose. So what happens if I pre-multiply this side with A plus BC transpose, the product will be the identity matrix, correct? So this, on this side, I get this. On the right-hand side, when I pre-multiply it with A plus BC transpose, I get this. Okay, and this must be equal to the identity matrix, I. So let's try to simplify it. This pre-multiplication helps us remove this, take care of this inversion here. Otherwise, it will be hard to manipulate, right? A plus BC transpose inverse is not equal to, for instance, A inverse plus BC transpose inverse or something. No. Anyway, so we have this. Now let's open up the this side. So we have A plus BC transpose, A inverse, negative, this times this, which is equal to this. So I got this here. I open up this, and then when I open up this is what I get. Okay, so now let's go to the next slide. So this is what I have. AA inverse is I, right? AA inverse is the identity matrix. So that's I plus BC transpose A inverse negative of this. This denominator, you know, is a scalar. Otherwise, you cannot divide. Now, then what I do is I see there's B on the left-hand side of both. I bring it to this side. And then I see C transpose A inverse is on the right-hand side. You know, in a matrix product, the order of the individual matrices or vectors, whatever, have to be preserved, right? So this has to be taken out on this side. What's left inside? B and C transpose. This is 1 plus C transpose A inverse B. I took out B on this side and C transpose A inverse on this side. And so what remains is C transpose A inverse B C transpose. No, just A inverse B. Excuse me. So this is what I have. Okay. Now, I just told you that you must preserve the order of the matrices in a product, with the exception of a scalar. A scalar you can move around. Okay. So this, you see this is a scalar. So you can just bring it outside. Okay. That's the only exception. Otherwise, you have to preserve the order. So I just got it here. Now you see this is a scalar quantity within parentheses, and that's equal to what's in the denominator. Right? So what can I do? Scalar and scalar, the two are identical. We can cancel them out. What I'm left with is this. Minus BC transpose A inverse. which is equal to I plus BC transpose A inverse minus BC transpose A inverse, which is equal to, these two cancel out, I get the identity matrix. Hence, proved. So this is what we proved. Now, common mistakes. Okay. This is a wrong approach. So suppose, okay, we were arrived at this stage, that's fine, and then we try to simplify it this way. We see that, oh, we have BC transpose A inverse on both sides, here and here. So we take BC transpose A inverse, and then we have 1 plus BC transpose A inverse. This is absolutely wrong. Why? For one thing, 1 is a scalar. See, again, the purpose is, okay, somehow to match the numerator and denominator or whatever, but 1 is a scalar, but BC transpose A inverse is a matrix. Okay. So you cannot add 1 to a matrix. There's a size mismatch. Okay, so this is wrong. 1 is a scalar, but BC transpose A inverse is a matrix. Okay, let's try another way. We could have correctly factorized it. Instead of 1, I could have written I here. You see, A, B, let's say there are two matrices A and B. A, B is the same thing as A, I, B, which is I is the identity matrix, right? That acts as a 1. In scalars, it's like a 1. Okay, so that's a matrix version of a 1, the identity matrix. Okay, so when I took this, I can take this out, BC transpose A inverse, but instead of writing a 1 here, I can write an I. Okay, but then what happens? It leads to nowhere. What do I do next? This is a matrix, and this is a scalar. I cannot do any cancellations or anything. So this, unfortunately, although this step is correct, leads to nowhere. We cannot simplify any further. So when you solve these problems, you need to strategize properly.